Why doesn't it happen? Share. And then, okay. You see it now?
Yes.
Control L. Okay.
Perfect.
Okay, Vlad. Thank you.
Okay. Thank you very much.
So let me introduce you. So our next speaker is Vladimir Gerdjikov with the talk Recursion Operators and the Hierarchies of Nonlinear or Evolution Equations related to Kac-Moody algebras.
Okay, thank you very much. The title is slightly changed, but the content is the same, actually. It is a great pleasure to participate in this conference dedicated to the 75th anniversary of my friend Andrei. And I would like to thank the organizing committee for this pleasure. So I will talk about Kac-Moody algebras and integrable equations. And my talk is based on several papers. The first two of them are seminal papers by Mikhailov, who introduced the group of reduction, and by Drinfeld and Sokolov, who introduced the close relation between Kac-Moody algebras and the integrable nonlinear evolution equations. The other papers are recent ones in which we obtained new results in this topic. So I will speak mostly about D4 type Kac-Moody algebras, and I will introduce briefly the notion of Kac-Moody algebras. Up to some central extension, the Kac-Moody algebra is the elements of the Kac-Moody algebras are elements of some simple Lie algebra, G, and they depend also on additional spectral parameter. So there will be some finite or semi-infinite sums over the powers of this spectral parameter lambda. The next thing we need to know about Kac-Moody algebras is that they are based on a special gradings of the simple Lie algebra, which is underlying the construction. The grading is done by its Coxster automorphism, which generically may have the form that it is a composition of the Coxster automorphism and at the element of the Weil group of the Lie algebra, eventually composed by external automorphism of the same algebra. And each time this Coxster automorphism is a finite order automorphism, so there is a number H, so that C to power H is the unit matrix. And H is the Coxster number. So if we consider the action of C in the root of spaces, in the space of roots of the simple Lie algebra, then of course it again will satisfy this C to power H equal to 1, and the eigenvalues Mk are determined by the numbers Mk, and these numbers are called the exponents of the Lie algebra. So using this finite order automorphism, we split the Lie algebra into direct sum of subspaces, which is called grading. And now each GK, each such subspace contains elements X such that when the Coxster automorphism acts on them, they get multiplied by omega to power K. So we can introduce bases in each of these subspaces by taking the average over the action of the Coxster automorphism, as it is here shown in equation 3. And an important fact that we have to know is that HP is different from 0 if and only if P is an exponent of G. From now on, I go to consider the simple Lie algebra SO8 or D4, and I start with the set of roots of this simple Lie algebra, and delta plus is the set of positive roots of it. There are 24 such roots there. The set of simple roots is given below, 4 of them. And I have to mention also that here I use a slightly changed definition of orthogonality, which is like that. X is an orthogonal matrix if S naught by X plus X transposed by S equals 0, and the matrix S0 is has plus and minus ones on the second diagonal as shown here. The Cartan-Weil generators of D4 are given here. Of course, the matrix is small e ij, such that they have only one non-vanishing element at position ij. Now, as most of you probably know, the algebra SO8 has two types of external automorphism. So we will consider these three cases. The first one, when we take as Coxster automorphism simply the element of the Weil group. And it is written here as the composition of reflections with respect to the simple roots. This Coxster, it has Coxster number 6, and the exponents are 1, 3, 5, and 3 again. The rank of the algebra is 4. Next, we consider the Coxster automorphism composed by the external automorphism of second order, which exchanges the roots alpha 3 and alpha 4. And here C2 is the composition of the Weil reflections composed by the mirror reflection, which corresponds to the external automorphism. The Coxster number now is 8, and the exponents are 1, 3, 5, and 7. The rank is 3. Finally, we can consider the composition of the Coxster automorphism with the external automorphism of order 3, the so-called triality relation. And then the Coxster number is 12, and the exponents are 1, 5, 7, and 11. The rank of this algebra is 2. Okay, let's do it one by one. So we start with the Coxster automorphism, which is an element of the Weil group. And when considered as action on the space of roots, it has this form, 4 by 4 matrix, and it's easy to check that C1 to power 6 is equal to 1. And now if we consider the action of this Coxster automorphism on the root system of D4, we get that it splits this root system into 4 orbits, but 6 elements in each of these orbits. They are given here. Now, we can check that C1 to power 6 is 1 also, and here are the explicit expressions for the generators in each of the linear subspaces, and here is the explicit form of these basis elements as 8 by 8 matrices. As you understand, they depend on omega 1, which is root for the six of the unit. Okay. When we consider the second type of Coxster automorphism that acts on D4 too, then we have to compose it with the mirror automorphism. Then it acts on the system of roots by this matrix. And now its eighth power is equal to 1. And the eigenvalues are these. Omega 2 is root for the 8 of 1. And the exponents are 1, 3, 5, and 7. Now, this automorphism splits the root system of D4 into 3 orbits, each containing 8 elements. So we can realize C2 also as a similarity transformation. And the fact that it's an automorphism consists in the fact that the determinant of this matrix that we are taking the similarity transformation is -1 rather than 1. Here is the basis in each of these subspaces, and the explicit form as 8x8 matrices is given here. Finally, the Coxster element for D4-3 is given by this composition, 2 while reflections with respect to the simple roots alpha 2 and alpha 1 times the triality transformation. And the triality transformation is such that it transfers the simple root alpha 1 into alpha 3 and then into alpha 4 and back to alpha 1. So this triality transformation in the space of roots acts like this simple matrix, and it acts on the corresponding while generators as it is shown here. This is not similarity transformation, so we have to take it as it is, of course. When we do the composition of the while reflections mentioned a bit above, with the triality transformation, we get this matrix as the action of C3 over the root system. And we have that C3 to power 12 gives the unit matrix. And now the eigenvalues are, of course, omega 3 to powers 1, 5, 7, 11. And omega 3 is root of order 12 of 1. Now, C3 splits the roots of D4 into only 2 orbits, each of them containing 12 elements. Okay, here is the basis also for these gradings. And now I'll start to tell you how these well-known facts from the algebra theory of D4 can be used to construct the Lax representation and the nonlinear evolution equations. So we construct the Lax representation. Lax representation is a set of 2 operators, cell and tem. They are ordinary differential operators, the first one with respect to x, the other one with respect to t. And the potentials in them, u and v, take values in the algebra D4. And the simplest possible non-trivial case is when u is a linear function of the spectral parameter. And so j is a constant element from the Cartan-sub algebra. And q is the corresponding potential of the Lax operator. V is polynomial in lambda, goes up to power n. And it is such that Q belongs to G0. Each of these coefficients, Vk, belongs to the subspace Gk. K, capital K, is the intersection of Gn with the Cartan-sub algebra. So we must have here an exponent of the algebra. And J, of course, is one is always an exponent, and it is non-vanishing. You will see it below. So this construction satisfies identically the definition of Mikhailov reduction group. So we have done a reduction which has this formulation, acting with the Coxster automorphism on U and also on V, will transfer the corresponding potential of the Lax operators into the potential where lambda is exchanged by omega lambda. And omega is root for the H of the unit. And what can we do now? Well, we can write down the compatibility condition. Remember that this compatibility condition must be must hold identically with respect to the spectral parameter. So each of the coefficients in front of positive powers of lambda must vanish identically. Using this fact, we can obtain recursion relations to construct the coefficients Vk in terms of Q. And in a while, I'll show you the answer, how these Vk are constructed in terms of Q. What remains to ensure is that the lambda independent term also vanishes. And we shall see that it vanishes if and only if the potential Q satisfies certain nonlinear evolution equation. We shall see these equations. So, sorry. When we do these recursion relations, we have to remember that taking the commutator with J has a kernel. And therefore, when necessary, we must split Vs into two parts, into a part which is belongs to the image of at J, and to the part which belongs to the kernel of at J. So when S is an exponent, we will have non-trivial sum. Vf will be different from V diagonal. And when S is not an exponent, well, there will be just Vf there. And in order to define the diagonal part of this, of the possible elements in Vs, we have to do some integration here, and we shall see the actual answer before. And for the off-diagonal part, we get this equation, which, of course, can be easily solved. And finally, we get that if S is an exponent, then Vs minus 1 is expressed through this recursion operator, lambda S, acting on the previous Vs of F. And lambda S is given by this expression here. So we have an integral differential operator, we have differentiation here, and we have an integral here, dx inverse. In case when S is not an exponent, then of course we do not have this integral part there, and we obtain only operator which I denote by lambda 0, and which is this operator. And in the special case, when we have before 1, we have an exponent which is double valued. This is exponent equal 3. And then we have here two such integral terms in the operator. Okay, so it is clear how to construct the Lax operators. What remains to be done is to calculate the corresponding evolution equations. I will do this formally here using the recursion operators, and here is the answer for this. So we can have a rather complicated, we have with each such Lax operator a hierarchy of nonlinear evolution equations, which of course is determined by the leading term of the Lax operator in the M operator. So here in D41, we have three possibilities. The first possibility is that the number n is equal to 6 times some other integer number, n0, plus 1. Then the result of this is this nonlinear evolution equation, where by bold-faced lambda, I have denoted the master recursion operator. It is a product of all necessary elementary recursion operators that are necessary to construct these equations. Second possibility is to choose n to be 6 times n0 plus 3. And then we have actually these two possible nonlinear evolution equations with different coefficients A and B here, because we have two different independent Cartan elements which belong to the subspace G3. These are H13 and H43. And finally, n can be equal to 6 n0 plus 5. And the result is this hierarchy of MKdV type equations. Here in the right-hand side, I have written down the dispersion laws for these equations. For the algebra D42, we have, of course, a different formulation, because now we have to distinguish between 4 different possibilities. N can be n times n0 plus 8 n0 plus 1 with this type of equations. Then 8 n0 plus 3 with this type of equations, plus 5 and plus 7, as you understand. And now the master recursion operator has this form. Finally, for D43, we get other 4 series of MKdV type equations. And of course, now the step is by 12. So 12 n0 plus 1, 12 n0 plus 5, 12 n0 plus 7, and plus 11, with the formal explicit form of all these complicated operators. Now the master recursion operator is this one, lambda 0, lambda 11, lambda 0 cube. Here we have a bigger gap between the two exponents, and therefore we have, here also we have lambda 0 to cube. Okay, these are the formal expressions for all these hierarchies. And what I will do now is to show you several examples of these equations. Of course, I will show you the simplest one also, only because most of them are rather complicated. All these equations are Hamiltonian ones, of course, and they have an infinite number of integrals of motion, and we have written about these Hamiltonian properties with Janowski about 10 years ago. And here is how their Hamiltonian structure is written down. Now, in fact, this is for typical Poisson brackets. However, our Poisson brackets are not so typical. So we have to use a Poisson bracket which involves dx in it. So actually our MKdV equations are written as have the right-hand side as x derivative of the variations of our Hamiltonians with respect to Q. And I start with the simplest non-trivial equations. These are the two equations related to D41 and having this dispersion law. So the first one, when when F1 is equal proportional to H1 3, then this is the set of these 4 equations, as you see. The second set of such MKdV equations are these ones. They are different, of course, and we can write down the Hamiltonians here. Now, some people think that in the seminal paper by Drinfeld and Sokolov, they contain, of course, a lot of Hamiltonians of integrable MKdV equations, but just these 2 Hamiltonians are not there. Actually, what Drinfeld and Sokolov had given as examples correspond to different gradings of D4. Now, the MKdV equations related to D4-2. Now, 3 is again an exponent of this algebra, and it is a simple exponent, not double-valued. So we have only these 3 equations, which are of 3rd order and are indeed KdV type equations. Here is the Hamiltonian of these equations. Finally, when we go to D4-3, we have to remember that now 3 is not an exponent. The lowest exponent is 5, and therefore what we get here is 2 equations, each of them of 5th order with respect to x. And you see they look rather complicated. This is the first equation, and this is the second equation. Here I have to mention that last year,
Excuse me, Vladimir, you have 5 minutes. You have 5 minutes.
Yes, I'll finish. Thank you.
Okay, thanks.
So last year, a Chinese student at the University of Loughborough completed her PhD thesis and derived a list of integrable 2-component polynomial equations. She used the method devised by Shabat, Yamilov, Mikhailov, and other people, collaborators. And she did really a very good work. And we had some difficulty comparing our equations with hers. But finally, we found that her equation under number 72 coincides with the set that I had just shown you here, up to a couple of coefficients. So both we and she had done difficult calculations. So I consider this as being equivalent, of course. The Hamiltonian of this system is given here. And we can write the same type of equations in another, also Hamiltonian-like form with 2 functions p and q. And now the functions p and q are given here. Okay, so I must say some words about conclusions. Of course, starting from a lax representation, it will be very nice if we could go to the end, solve the direct and inverse scattering problem, and eventually construct even the soliton solutions. Solving the direct and inverse scattering problem is, one can say, has been done. It had started by a seminal paper by Shabat, who devised the notion of a fundamental analytic solution. And this was done for the simplest non-trivial case when J has real eigenvalues here and when the analyticity properties are rather simple. You have one fundamental analytic solution in the upper half plane and another in the lower half plane of the spectral parameter lambda. Using these fundamental analytic solutions, Zakharov and Shabat then derived the famous dressing method for deriving the soliton solutions. So this was also very good news. Then about 10 years later, Bills and Koifman were able to construct the fundamental analytic solutions for Lax operators, generic Lax operators, where J has complex eigenvalues. And then later, me and my co-authors were able to generalize these results to the cases when L is an element of a simple Lie algebra and J has arbitrary complex values. Finally, in 2014, with Janowski, we constructed the fundamental analytic solution for Lax operators, which are subject to ZH reductions. And let me show you what is the result. The result is that the continuous spectrum of the Lax operator, which is relevant for D41 algebra, consists of these 12 rays, which go to infinity. And then we have 12 sectors. In each of these sectors, you can construct fundamental analytic solution, and we can write down the corresponding Riemann-Hilbert problem. And of course, this means that the fundamental analytic solution in sector nu is related to the fundamental analytic solution at sector nu plus 1 by these Soing functions. And these Soing functions are related to something that could be called spectral data. Actually, they could be called spectral data for the Lax operator. I do not have the chance to explain everything in details, but when we consider this rays, we have to take into account also that to each ray we can relate subsets of roots. And for example, when we have D41, with all even rays, we relate a subset of roots, actually one root, two roots actually. The root and it's negative, it forms an SL2 subalgebra. In the odd numbers of rays, we connect a subalgebra which is a direct sum of 3 SL2 subalgebras. When we have D42, then again we have similar construction, but now one algebra SL2 is related to the even rays, and for the odd rays we have sum of 2 SL2 subalgebras. When it goes to D43, now we have 24 rays. And with each ray, we define just one SL2 subalgebra. This is also very helpful and gives us also the chances to derive action angle variables in terms of the scattering data of the corresponding Lax operator. And this is relevant also to one of my last remarks, that actually the inverse scattering method is a generalized Fourier transform. This was devised as an idea by Ablowitz, Kaup, Newell, and Seeger 40 years ago nearly. And it is true also for these complicated systems with deep reductions. And finally, of course, one could easily guess that it might be possible to apply the dressing method to construct the solutions, the soliton solutions for these MKdV equations, and also for the two-dimensional Toda field theories, which belong to the same hierarchy as the MKdV equations here. And really, I tried to do, but still could not go to the end, because due to the deep symmetry, the dressing factor that would allow me to calculate the one soliton solution must contain 24 poles. And it makes the problem a little bit technically difficult. But I'll continue. Maybe next time I'll be able to construct the report about this. I would like to thank you for your attention and to say happy anniversary, Andrei. Have a lot of luck and great scientific success. And I would like to remind you, I think you should remember how we celebrated your birthday 40 years ago in Primorsko. Do you remember that?
Great, thank you very much. Yes, of course I remember.
It was the birthday
nice.
of Andrei, Sasha Zamolodchikov, and Mikhail Polivanov, late Mikhail Polivanov.
Exactly.
Yeah.
Yeah.
So thank you very much.
Thank you very much. Thank you.
Thank you. So please, questions.
May I ask a question?
Yes.
Yes, sure.
Oh, Vladimir, so there is a point I would like to have information. How do you control the commutativity of the Hamiltonian equation you obtained this beautiful scheme? How you have shown that the equations are Hamiltonian, you have a hierarchy, but how do you control that the equations commute?
You mean that the
laws are commuting.
Integrals of motion have vanishing Poisson brackets.
If you like, it is the Hamiltonian or that just as the operator commutes.
Yes, 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 I understand. Now, this is based on the fact that we have generalized Fourier transforms. And actually, we can, doing these generalized Fourier transforms, we expand everything in terms of the eigenfunctions of the master recursion operator.
So you could just control after you pass to the scattering data. Before you don't control.
Everything is a well-bounded technology, so to say. Now, I can do the expansions not only of the potential over this squared solution, so I can develop over them also the variation of the potential. And as a result, I can also derive the expression for the basic symplectic form in terms of the variations of the scattering data.
Okay.
And then I can devise also the hierarchy of symplectic forms through the master recursion operator.
Mm-hmm.
The master recursion operator multiplies the squared solutions by the by the power of spectral variable. Then what I see is that the densities of these symplectic forms are all different by powers of lambda.
Mm-hmm. Okay.
Therefore, they must be absolutely compatible. And your construction that you devised for the MKdV is extended in a natural way also for all these generalizations of KdV.
Thank you.
Okay, thank you very much. We are slightly out of the schedule, so let's finish